For each integer n, compute the smallest possible value of the sum from k equals 1 to n of the floor of ak over k, over all permutations a1 through an of 1 through n. So let's experiment a bit. So what happens if ak is equal to k for all k? In which case we just have a1, a2 all the way to an is just 1, 2, 3, 4 all the way to n. Then the sum is clearly just 1 plus 1 plus all the way to plus 1, which is n. But it definitely feels like we can do better than that since there are so many other permutations which we haven't covered. So I'm going to go ahead and write it out for n equals 8 so that it's easier to describe the thought process. All right, so now I've written out each of the terms, and now we can observe what happens. So we just noticed that when we let it be 1, 2, 3, 4, 5, 6, 7, 8, then we just get the number n here. But what happens if we swap these two last ones? Because if we have a value smaller than 8 here, then this one just vanishes. So if we do that, then we get 8 and 7 here, and that achieves a value of 7, because now we have this. But now we can just try to continue moving the 8 down, because when we try getting the 6 over the 7, then that also gives a 0. So let's try to keep decreasing this as long as we can. So this becomes 8, 6, and 7, and then we end up getting 8, 5, and 7, 8, 5, 6, 7, and this ended up giving a value of 5. However, if we try swapping the 8 and 4 now, then even though we get 4 over 5, we get 8 over 4, which is 2. So that does nothing to help. So we should probably not move the 8 down any further. So now we have 5, 6, 7, 8 among these last guys. So now we have 1, 2, 3, 4 among these guys. And we want to try minimizing this part, which is just an earlier instance of the problem. So we can try doing the same thing. So we swap the 4 and the 3. And then we can't move the 4 down any further. And then we similarly can't move the 2 down any further. So we have this sum here, and this gives a value of 4. So it makes sense that 4 would be the minimum for the 8 case. So let's see if we can generalize for the n case. So, and there are definitely some cases that we have to consider of whether n is even or odd. So if n is even, suppose n is equal to 2k, then we can just repeat this thought process that we have over here, where we have 2k over k plus 1, and then k plus 1 over k plus 2, and then so on all the way to 2k minus 1 over 2k. And that contributes a total of 1. So if we let a of x be the answer for x, then a of 2k, we hope, is equal to 1 plus a of k. And then if n is equal to 2k plus 1, then we can end up using 2k plus 1 over k plus 1, and then k plus 1 over k plus 2, and then so on all the way to 2k over 2k plus 1. And we end up getting that a of 2k plus 1 is equal to 1 plus a of k. And we immediately notice that this is a logarithmic type of thing, and obviously we should remark that a of 1 is equal to 1, obviously, and a of 2 is equal to 2. We can just bash those cases out. And so again, we expect it to be logarithmic base 2 or relate to binary representation. So maybe we'd expect the answer to be log 2 of n plus 1 or something like that. And we add the plus 1 here because we have n equals 1 gives it to 1, and n equals 2 makes it 2. So, and this definitely appears to satisfy our relationship. So we conjecture that this is our answer. And we have a construction for this, but we still need to prove that we cannot do better than this. So now we have our answer and we have a construction, so now we need to just show the bound. And one idea we have for the bound is to try proving it inductively again. So let's split it into cases again. So we have n equals 2k, then that means that we have the first few k terms of the sum, so that's a1 over 1 plus a2 over 2 plus so on and so forth, plus ak over k, and then we have ak plus 1 over k plus 1 plus all the way to plus a2k over 2k. Then we know that by the inductive hypothesis, we're going to just induct here, that this thing here is at least log 2 of k plus 1. And we have that this here thing here is floor of log 2 of 2k plus 1. We want to show that this expression is at least this, so, which is just this expression here plus 1. So the only way we can fail really is if we have that, let me erase this here, is that we have that this is equal to log 2k plus 1 and this is equal to 0. So under what circumstances is this equal to 0? Well, we have that, for one, that there's no 2k among these terms, so we can't have any of these terms is equal to 2k, otherwise we get this, the expression is at least 1. So therefore, the 2k must be among these guys. But then when we have 2k over 1, then that is just 1 plus 2k minus 1 over 1. Similarly, if we have 2k over 2, that is just equal to 1 plus 2k minus 2 over 2. And you get the idea. We go all the way up to 2k over k is equal to 1 plus k over k. And each of these guys still works, and each of these guys is at least equal to the denominator, so we don't run into any issues here. So basically, what we are doing is, in the 2k term, we are subtracting 1, and we are still getting a term that is larger than the denominator. So we have, if we have a term that's at least as large as the denominator, then we can just like scale it down to the permutation. So for example, if we have k equals 4, then we have 1 over 1 plus 8 over 2 plus 4 over 3 plus 3 over 4. Then we can scale this 8 down to the 2. And similarly, if the 8 were here instead, then this 8 can be scaled down to the 4, and then this 4 can be scaled down to the 3. So we have the scaling down idea, and the scaling down does not increase the sum. But we just showed by the induction that this sum here is at least this expression here. So whenever this expression here is 0, the expression here must be this sum here plus another 1, because we had to take it down and then scale it up, which makes it a plus 1, and that gives our bound for n equals 2k. The bound for n equals 2k plus 1 is very similar, and I'm not going to go through it here, but I encourage you to work through the details yourself, as it's rather instructive. Therefore, we have arrived at the answer log 2 of n, floor of that, plus 1. So what can we take away from this problem? Well, for one, we should try looking through small cases like n equals 8 as we did earlier. And whenever we want to try minimizing something, look for degrees of freedom that you can try using. For example, when we use n equals 8, we move the 8 from the end all the way to the middle, because and that kept decreasing the sum. So you're trying to just decrease it just as much as possible at every step. In other words, we're changing things locally. And after we arrive at our answer, the answer is probably one of the hardest parts of the problem. After arriving at it, we can just use the recursive nature of the answer. If we have a log 2 of n something, then we want to try using induction whenever possible. And induction ends up helping here, as we see. So thank you so much for watching this video. Please subscribe if you'd like to see more.